Good. So in this lecture, we are going to talk about phylogenetics and the development of classifications, but more specifically looking at how we analyze data that we get from sources of taxonomic information and produce trees that can be used then to be drawn into a classification system. So a useful classification has these characteristics. Predictivity, we've spoken about predictivity before, where new characters tend to agree with the position of taxa in the system. We, in the practicals, are looking at families, and remember that we said that each family is defined by a set of characters. So if you find an unknown plant that agrees with those characters of those families, we can assume that it belongs to that family. So it is predictive in that way that, you know, the characters agree with the families, and we can then place taxa in those families. It's comprehensive, so it must include all taxa, and taxa that have not yet been described must be described upon discovery and included into the classification. It must be consistent. Criteria for determining the position of taxa will be the same for all taxa. You can't have any exceptions, and therefore the consistency is really key in classification. New data can be accommodated. So if you discover new taxa, they can be easily added into the system without messing up the whole system. If new taxa are not easily accommodated into the system, then there is some problem with the classification. Traditional methods in the past, as we've seen when we looked at the history of classification, morphological data was the main thrust. But we have modern techniques, we went through all of these that have been added: chemical data, cytological data or data from chromosomes, and then DNA studies, and they lead to new insights into relationships between taxa. And they can point out where in the past people have gone wrong with classification systems. So remember, when we sequence the DNA, for example, and we build trees, we really get a good idea of true relationships between taxa. And often if we only look at morphology, then those relationships we get wrong because of things like convergent evolution. Classification systems are then continually modified to accommodate new information, and modifications to the circumscription and ranks of taxa should only be considered if it would lead to improvements of the system. So that's important. We don't just change classification systems for the sake of changing them. They need to stand the test of time, but they also need to be improved in order to be as good as they can be. So in modern times, two different approaches are used: phenetic and phylogenetic, or cladistic, and we are going to look at these two in turn. And the idea is that we objectively refine classification systems and phylogenetic classifications, so that we can say that these are based on the analysis of empirical data. So the first, phenetic classifications, is also called numerical taxonomy, and it follows the principles set out by Sneath and Sokal in 1973. And these principles are that the more characters that are used, the better the classification system. This is true also for phylogenetic systems. All characters have a priori, or at the outset, the same weight. After the fact, or a posteriori, weighting sometimes can be done to emphasize some characters that are more important for some groups than for others. The overall similarity between two taxa, which is what we try to calculate in this analysis, is a function of all the individual similarities in a large number of characters. So the more similarities in characters two individuals share, the higher the overall similarity between these, and the more likely they are to sit next to each other, or together at least, in the tree. Discrete taxa can be distinguished because characters are differently correlated in different taxa. This is just the idea then that a species would have at least one or two things that makes it unique. So those differences you'll find between species, but then species of the same genus would share things again, which would mean that they group together. Phylogenetic deductions can be made from the phenetic structure if certain assumptions are made about the evolutionary process. So typically phenetic analyses are not used necessarily to infer evolution, because it is not based strictly on ancestral relationships between taxa. Taxonomy is viewed in practice as an empirical science, which is why we are doing this analysis, and classifications are based on phenetic similarity. So the process I'm going to go through, and I don't expect you to specifically know this. We are going to look at the phylogenetic one in more detail, but this is just good to compare the two. So the first is we decide on the species that we are going to use, and these we call operational taxonomic units. We choose characters, and as we said, in this case, the more characters the better. So phonetic classifications and phonetic analyses use lots, often hundreds of characters. And the character states are then decided, and you compile a OTU by character matrix. I'll show you an example of this just now. We calculate the similarity between all the pairs of the OTUs by using a similarity coefficient, which is a mathematical equation. So this is often done using computer software that will calculate this. And then you compile an OTU by OTU matrix, or a similarity matrix, which compares the pairs of OTUs. And then it goes through a process of cluster analysis. So remember, we said here that we are trying to calculate the overall similarity. So this process of clustering will do exactly that. It will calculate the similarity between the OTUs, and it will cluster those that share more characters or have a higher overall similarity together. And it does this in the shape of a dendrogram or a tree. In this case, it's called a phenogram because it's the product of a phonetic analysis. And then from that phenogram, we can draw up a classification. We interpret the phenogram and use the phenon lines, which are the lines of the tree, to distinguish between phenons. So there just some guidelines. The choice of OTUs, it must be representative obviously of the full range of variation to be studied. So we often look at several populations per species in order to polarize the characters and decide on the characters. OTUs are the smallest units in a numerical study, and they are mostly individual plants, but can also be populations, species, or genera. So the choice of characters, the more characters the better. At least 60, 80 to 100 are preferable. Variation within an OTU must be smaller than the variation between OTUs. So remember, we said that we can't have too much variation within a species, or more variation within a species than between it and other species, because then it's not a good species. So the species need to be consistent in their characters, and to allow us to compare between them and other species. Logically correlated characters should not both be used, and we typically use binary characters, so presence or absence, and these are coded for 0 for absent and 1 for present. Multi-state characters are logically coded from 0, 1, 2, etc. So often you can have several flower colors, for example, so white, blue, purple, etc. So these you code depending, and you can have many states, say up to 5 or 10 character states. Quantitative characters are directly quantified, so dimensions, if you measure the length of the leaves or those kinds of things. Qualitative characters can also be quantified, but it can be done in different ways. So flowers white versus flowers pink, pale pink or dark pink. We can also make multi-state characters to two-state characters. So if we take this example, we can just have flowers white versus flowers pink. So it doesn't matter in some cases whether it's pale pink or dark pink. The OTU matrix, all numerical values which were allocated are now entered into this OTU by character matrix. Calculation of similarity with the coefficients. We have two types, the distance coefficients and association coefficients. I don't expect you to know the details of these, so don't worry too much about this. The similarity between all the pairs of the OTUs are now entered into an OTU by OTU matrix. So this OTU matrix is normally a symmetrical matrix, and you can see that we can then compare all the pairs of the OTUs using this matrix. Then the process of clustering happens, and three basic techniques can be performed: single linkage clustering, complete linkage clustering, or average linkage clustering. Again, I don't expect you to know all of this, but basically it calculates the degree of similarity across this whole matrix. So where we can have lower similarity between some pairs and high similarity between others. And then it draws these phenon lines based on the percentages that were calculated, and the clusters are then drawn up from the similarities that were calculated. And then we get what we call the phenogram, which is a tree drawn up from this clustering analysis. So you can see here is the similarity coefficient, and here are the phenon lines that are drawn to join the different phenons or taxa at the end. In this case, you can see this was a population level study, and it was trying to discover how many species were in this population. And you can see here each cluster then represents a particular species with several of the populations that were analyzed or for which characters were coded. So this is just a summary. So you choose your taxa, you choose your characters, and you polarize that from 0, 1, 2. So it's things like presence or absence, length of leaves and stems, flower color, seed length, etc. And we then do a character by OTU matrix. A similarity criterion or similarity coefficient is used to produce an OTU by OTU matrix that goes through a clustering analysis, and it draws up a dendrogram or a tree. And this is then translated into a classification. This contrasts then to phylogenetic or cladistic analysis. And cladistic analysis started with Willy Hennig in the 60s, and the term cladistics was first used by Meyer. The use became very popular very quickly, and new developments are constantly published still today. And it's viewed as a method to obtain objectivity in phylogenetic classification. So again, similar to the phonetic, which was also for objectivity, and again, an empirical approach that is followed, similar to the phonetic analysis, so that methods can be repeated and verified. Cladistic methods differ from phonetics in that overall similarity is not necessarily regarded as a reliable measure of affinity, because overall similarity can also mean that you have things that are similar because of convergent evolution, for example. The basic principles, so these you should know, and you should be able to compare it to the principles of phonetic analysis. So you can see that these are quite different, and here a strong emphasis is placed on evolution. So taxa in a phylogenetic system should be monophyletic, and para and polyphyletic groups are not acceptable. We distinguish between primitive and advanced character states. So those are also called plesiomorphic or apomorphic character states. Taxa, which are your clades or monophyletic groups, are recognized on the basis of shared apomorphic character states, shared derived character states, which are also called synapomorphies. So we are not interested in the primitive characteristics that are shared between a set of characteristics, a set of taxa, but you are interested in those that are derived or represent adaptations or changes. So the monocots, for example, that lose a cotyledon, or the angiosperms that all of a sudden develop a closed ovule. So those are the kinds of derived changes that we are interested in. Shared plesiomorphic states are meaningless. And the most parsimonious or shortest cladogram, the one with the smallest number of steps or the smallest number of changes, is the one that is accepted. So the solution that requires the smallest number of hypotheses about the character state changes is preferred. So that's what's meant with most parsimonious. Advantages is that the method can be repeated, every step is verified and subject to critical evaluation. Method has practical value because even a few characters may give a meaningful result. So you can see it's not as labor intensive as phonetic analysis. So remember where we had 60 to 100 characters. Here a few characters are already meaningful. Results can be obtained manually and are readily visualized. The taxonomic pattern on empirical data can be studied without involving assumptions about phylogenetic processes, and new insights may be gained into relationships of the taxa. So in order to understand the trees and phylogenetic analysis, there are some terminologies that you need to get to know, which I've listed here, and you need to learn these and know them off by heart. An apomorphy, which is a derived or advanced character or character state. Homology. Two or more characters are homologous if they share a common ancestor. So they're directly comparable to each other. This is in contrast with homoplasy, that are non-homologous similarities resulting from convergences or reversals. So when you have, again I use the example of red flowers. Red flowers are present throughout flowering plants, and they develop in a response to a pollinator. So they are not the product of a shared evolutionary ancestry, but rather due to some selection pressure. So those are homoplasious characters. Cladogram is then the tree that we draw up, a two-dimensional representation of the phylogenetic or branching pattern. Convergence, when the same apomorphy arises independently in two or more different lineages. So we've spoken about that here with homoplasy. Then monophyletic, a group in which all the members share a common ancestor and it includes all of the descendants. And they normally have at least one convincing apomorphy. So here you can see the root of the tree, and this, for example, would represent a monophyletic group. The trees itself has some terminology. Root of the tree, these are the nodes and the lines joining them, internodes. The branches are those right at the end, and then the tips are the taxa. So here we can see again examples of monophyletic groups there and there. We can have it at different levels. Paraphyletic groups, so those are ones where all the members share common ancestor, but not all of the descendants are included in the particular grouping, as you can see there. M and C, for example, are not included. And then polyphyletic groups, a group where the members do not have a common ancestor. So in an A, for example, and they are not derived from a common ancestor at the nearest branching point. Autoapomorphy is an apomorphy that is unique to one terminal taxon, and this is true for all species. We assume that all species at least have one autoapomorphy. Plesiomorphic primitive state, polyphyletic, we've spoken about. Reversal, when a derived feature is lost and replaced by the original condition. So we can have cases where you have a group of species that have a particular adaptation. Say they go from white flowers to red flowers, but then due to some pressure, some of the species can switch back to having white flowers. So remember that the genetic pathways are not lost, so you can always have reversal to the original or the primitive state. Sister groups, two taxa that sit together and share an immediate ancestor. Synapomorphy is an apomorphy which defines a monophyletic group, so a character that is shared by all of these taxa, for example, would be a synapomorphy. And topology is then the branching pattern within the cladogram. We are going to then draw simple trees, so we're going to go through the process. So first is the selection again of the study group and the choice of outgroups. This is similar to what we did in the phonetic analysis. Again, we polarize the characters, giving them numerical numbers 0, 1, 2, 3. Assign polarities to all the character states that can be logically polarized. And this logical polarization we do by deciding which characters are primitive or plesiomorphic and which are derived or apomorphic, and we assign numerical numbers accordingly. Plesiomorphic we normally score as 0, and then the apomorphic we normally give 1, 2, 3 depending on how many there are. We then tabulate the data in the form of a taxon character matrix, and this differs from the phonetic analysis in that we only have one matrix that we set up. We then construct the most parsimonious or the shortest cladogram from this, and this can be done through logical reasoning, an algorithm or computer program. Most often we do this with computer programs, but we are going to do this manually through logical reasoning. And then we examine the assumptions and we produce the most well supported cladogram. And we have symbols that we plot onto the tree, apomorphies that we indicate, and also convergences, reversals, and autoapomorphies, those unique to species. So this will become more clear as we work through an example. Study group must be monophyletic, and it should have at least one synapomorphy. So all of the members of the particular group should at least share one character. And all the members of the group must be included. If some are not included, then it's obviously paraphyletic or polyphyletic. The characters must be logically polarized from primitive to more advanced. They must all be homologous, so it means they must all be descended from a common ancestor. Sometimes detailed studies are necessary to determine homology, unless there is evidence to the contrary. Polarizing characters for each character determine whether it's plesiomorphic or apomorphic. The character states are arranged from least to most advanced, and numerical numbers assigned. So as I said, plesiomorphic normally 0, apomorphic 1, and it can go 2, 3 depending on how many there are. And this sequence of characters from primitive or plesiomorphic to more advanced is called a morphocline or a transformation series. So there are different ways in which we can polarize, so deciding on what is primitive and what is advanced. It's not as simple as it sounds. Often we can compare to fossil evidence, because sometimes the ancestors would be in the fossil record. Ontogenetic studies, where we look at juvenile stages to decide whether things are homologous and what is the primitive state and which is the advanced state. But what we are going to use is the outgroup method. Characters of a study group are compared to a closely related group, and this should ideally be the sister group to the study group. We then assume that states unique to our study group are apomorphic, and states that occur in the outgroup and in our study group are plesiomorphic. So we will do intuitive polarization, and obvious specializations are accepted then as apomorphic or derived. And normally hypotheses of each and every character are drawn up so that we understand the transformation series that we are building. The taxon by character matrix, we then set up numerical values that were assigned are entered into the matrix. So the outgroup, which is the one that we compared with, will have 0 for all of the character states, because remember we said here we assume that those that are present in the outgroup will be plesiomorphic, and therefore 1 will be scored as 0. And then some of your in-group can also have the plesiomorphic states, and they would then be scored as 0, but all of the apomorphies would be scored as 1, 2, etc. And if we have mixed states or multiple states in some taxa, those will be scored as 0 and 1, or whatever the states are. So finding the most parsimonious cladogram can be done again through logical reasoning, algorithms, or computer program. This computer program is called PALP, but we will manually do this and look for the cladogram with the smallest number of steps. So often we find several trees that can be drawn by different interpretations of the characters. But we will look for the shortest one, and that will be the correct one. Okay, so we will go through this example, and this is the kind of thing that will be asked in the exam. So I give you a set of taxa. You can see here A, B, C, D, and E. And these you can see are all slightly different. Some of them share characters, they are more similar looking. And then I always will give you the outgroup or the hypothetical ancestor to this group. I then number the characters, and remember a character can have several character states. So in this case the character here is leaf arrangement, and you can see that the leaves can either be alternate to each other or they can sit opposite to each other. So this character, which is leaf arrangement, has 2 character states. Because the alternate leaves are present in the outgroup, we would assign that as 0, and the opposite would then be 1. We can then look at number 2, which is the PTL, whether the PTL is present or whether it is absent, so 0 and 1. Then we have thorns, number 3. So again, whether the thorn is present or whether it is absent, and we can see thorns are present in the outgroup, so 0 and 1. Leaf shape, we have broad leaves or narrow leaves. Broad leaves are in the outgroup, so that would be 0, and narrow leaves would be 1. Flower size, small flowers and large flowers. So small flowers we can see are present in the outgroup, so that would be 0, and then large flowers 1. We then, number 6, have bracts on the flowers, whether they are present as in the outgroup, which is 0, or whether they are absent, which is 1. And then we have a multi-state character here, in the inflorescence. We can see that we have 3 flowers in an inflorescence in the outgroup, 2 flowers in some of these, and then 1 flower. So remember, we are doing logical polarization. So you won't go from 3 flowers to 1 flower and all of a sudden jump back to 2 flowers. If you are going to lose flowers over time, or have a reduction in your inflorescence, you will do that in a logical progression. So we would go from 3 flowers to 2 flowers to 1 flower. 3 flowers present in the outgroup, so 0, 1, and then 2. Make sure that you understand this process, because this will be important for you to do before you move on. So this is the logical reasoning and the polarization. If you're not sure, go and look through the methods again on the previous slides. So now we have to set up a character by taxon matrix, and we put these values in. So this is what it would look like. Here's your outgroup. Here are your taxa that you list, and here are your characters 1 to 7. Remember, what you immediately should do is you should put in 0 for everything for the outgroups, because the outgroup, as we said, will always, we assume based on our method, that is the plesiomorphic or primitive state. So then you go and look now in at each character in each taxon. So taxon A, you would see has opposite leaves, so you would put a 1. Taxon B also has opposite leaves, a 1. C, D, and E, you can see all of them have opposite leaves, so all of them would be assigned a 1 for character 1, because they all have opposite leaves. And immediately you can see that this would be a synapomorphy, because remember we said that there has to be a synapomorphy that is present in all of the taxa that we are studying, but not present in the outgroups. Number 2, the PTL, we can see that the PTL is present in the outgroup, so that would be 0. So A and B have lost their PTL, so they would be 1. But C, D, and E have retained their PTL, so they would be scored 0. Then the thorns are present in A and B, so they would be 0, because the outgroup also has thorns. And then for the others that have lost their thorns, we would give them score them a 1. Number 4, leaves. We have narrow leaves in A and B, so they would each get 1. And then we have broad leaves in C, D, and E, so they would get 0, because they are like the outgroup. Number 6, or number 5 first, the flowers are large in C and D, but in all of the others they are similar to the outgroup. So C and D would get 1, and all of the others would get 0. Then bracts, you can see that A has the bracts, D and E has the bracts, so they are like the outgroup, so they would get 0, and only B and C would get a 1. And then the multi-state character, so if we go and look which ones would get 0, A and B are like the outgroups, so they would be scored 0. E has 2 flowers, remember 2 flowers is 1, so we would give it a 1. And then C and D have 1 flower that we said is 2, so we score them at 2. So now what we have to do is we have to draw this into a tree. So first we look at all of the individual characters. So remember that you need to go and look at these symbols. So apomorphies without homoplacy, if it's a synapomorphy, you would give it a square. convergence is an equal line, reversal across an autapomorphy, a circle. So we are now going to look, so character 1 is present in all of the taxa. So you can see there. For character 2, only A and B have that character, so you would give that's an apomorphy there. Character 3, C, D, and E. So they are joined by character 3. A and B, C and D for character 5, B and C for character 6, and then the multi-state character. So we know that C, D, and E all have a change in their inflorescence, so meaning that they have some kind of reduction in the number of flowers. So remember that we said you would first go from to 2 flowers and then to 1 flower. So you can see that we have this character twice. So number 7 is some reduction in the number of flowers. E has lost one of its flowers, but C and D share a further character in that they have lost another flower. So they would then be grouped because they only have a single flower. Okay, so this process again is important, interpreting this into the tree. So now what we can look at when we look at these is we try to see which of the taxa are more similar to each other. So we know that we have character 1, which groups all of them together, A, B, C, D, and E. But we see that A and B share 2 characters with each other. C and D share these 2 characters, and C, D, and E grouped together by these characters. So we would assume then that A and B are sister taxa, and then C, D, and E grouped together, but C and D are more closely related to each other than they are to E. Okay, so we draw A and B together, then E, and then C and D. Now we put these symbols of our characters on there. We have character 1 that groups all of them together. A and B share characters 2 and 4, so we draw those blocks on there. C, D, and E have character 3 and 7 that they group together. And then C and D have 7 and character 5. So now we see that B and C share character 6, but B and C are not sitting together on the cladogram. So we can see that this character obviously is convergent, so it's not from a common ancestor. So we draw that with our equal sign. Okay, then we can count the number of steps in this tree to determine the length of the tree. And for that we count these character blocks that we've put in: 1, 2, 3, 4, 5, 6, 7, 8, 9. So this cladogram has 9 steps. Okay, we will do more of these kinds of exercises, and you can also go and look at old exam papers. But when we have online sessions, we can also look at these together. So phylogenetic analysis are very large groups of taxa, are obviously not as simple as what we've just done, and you won't draw those by hand. DNA matrices can then be analyzed in 3 different ways. We have parsimony analysis, maximum likelihood, and Bayesian analysis, and this you'll come to know as you move through the BDC courses. We'll do this in more detail. And each of these has a different computer software that implements these analyses. And they also then, the aim of each of these is to produce a tree that can be interpreted into a classification. So parsimony is based on what we just did. So the shortest tree is the correct tree. and the one with the fewest number of changes. Maximum likelihood tries to infer the tree that maximizes the probability of observing the data, so the tree that is most likely to have been or to represent the data on hand. This uses models of evolution to select the most likely tree. And Bayesian analysis is based on posterior probabilities. So probabilities are estimated based on, again, a model of evolution. And these probabilities are higher than for taxa that share certain characteristics, and they would then be placed together within the tree with high probability values. So as I've said, that classification systems used to be based on morphological characters, but over time we've added, as we saw when we went through the sources of taxonomic information, we've added anatomical data, data from chromosomes, chemical data, but most importantly we've added DNA data. And DNA data have really revolutionized classifications, because we have an insight into the real relationships between taxa by building phylogenetic trees. And then we can refine our classification systems based on these data. So there have been very large projects that have sequenced DNA across flowering plants and other taxa. And the angiosperm phylogeny group is one that worked specifically on flowering plants. So the idea here was that it's an informal group of systematists from across the world that came together to study the taxonomy of flowering plants and look specifically at higher level relationships, normally above families and above. And they started in the 1990s and have published 4 versions of the classification over that time to the present. And their classifications are widely accepted, although there are some problematic areas. So the principles here is that Linnaean system of orders and families should be retained, and they follow Linnaean classification, meaning they follow the binomial, they follow the code of nomenclature in that we recognize families and orders, and they follow the suffixes that pertain to each of those. And an ordinal classification of families is proposed as a reference tool of broad utility, and the orders are considered to be of practical value in teaching and in studying family relationships. Groups are monophyletic, as with the phylogenetic and cladistic criteria. And a broad approach is taken to defining the limits of groups, such as the orders and families. So this is one of the problems, that they have very broad concepts of what families are. And sometimes we have small families, highly specialized families, that then get lumped into larger families, which for some countries is a bit problematic. So they don't have families containing only a single genus or orders containing a single family, although this is not necessarily the correct procedure. And then they only follow Linnaean classification to the level of orders, and above that they have informal nomenclature that they apply to groups. I'll show that to you now. So these are the 4 classifications that have been published, and they are APG 1, 2, 3, and 4. The most recent in 2016, and each one is slightly different to the next. So you can see that they list the orders, and within the orders they have the families that are recognized. So they in the most recent one recognize 64 orders and 416 families. This is the tree from APG3, and you can see here that it includes all of the flowering plants. Here's a simplified version where we have seed plants with gymnosperms sister to your angiosperms. And then this is basically what they show. So they show then that monocots are derived from within the dicots, and we have the Magnoliaceae and some other taxa that are the most primitive or least derived of the angiosperms, and then we have what is called the true angiosperms that are represented here. And each of the families has specific morphological characters that define it. So it is still, morphology is still used in combination with the DNA to draw up these classifications. This is from APG4, just a refinement of some of these. As I said, we have the orders that contain a bunch of families, but above these we have an informal taxonomy. So monocots, for example, magnolids, comelids, that is recognized or used at higher levels. So we have ranking here up to the level of order, and then unranked above the level of order.